Okay, welcome everybody. Thanks for coming. This is the week 10 webinar. So we're almost done. There's this week and next week. This is the last Monday webinar of the quarter because next week it'll be Tuesday and then it's over. So just let you know, this is the last webinar, the second to last webinar of the entire quarter, and hopefully it's going well. And I always, recommend you pay attention to it because if you don't use the wording I tell you, then you lose points and also you learn a lot. And I recommend taking notes too, just so you see it all. So let me tell you the plan today. And the plan is always I'll answer any questions that you might have, and I'll always be watching the chat box and answer whatever you need. And then today and this week is all about regression analysis. Turns out to be a really, really, really important topic that comes up in lots of applications. And we're only going to be doing single variable regression analysis, not multiple variable regression analysis. So if you take, more advanced stats class, you'll see more details, and only linear regression analysis is what we're going to do. So there's a lot more to it than just what we're going to do, just let you know that. So what we're going to be looking at are some of the key pieces. One are scatter plots. I've mentioned scatter plots before, but now we're really going to get into them. And then this sounds easy, it's just a letter, R. But R is going to be called the correlation. You've probably heard that word before. And we'll talk about that and how do you interpret it. It's going to be a lot of writing in this. Then we'll look at R squared, which mathematically is literally R times R. But it turns out it has very special meaning also. And we'll talk about that today too, in terms of what that's all about. We'll look at the equation of the regression line, because that's a big part of regression analysis, is to find a line. And hopefully you remember a little bit from your beginning algebra classes that y equals mx plus b, for example, that how to find the equation of a line and what it is. And then we're going to be looking at the slope of the line and how do you interpret the slope of the line based on what you have. And we'll also look at the y-intercept and can you interpret that? Then after that, we will talk about what you can and cannot conclude based on regression analysis. And the biggest is causation. So avoid causation. I'll mention that many times. And then finally, hypothesis testing. I did promise that the entire last half of this class, we're going to be doing hypothesis testing. So we're going to be looking at a hypothesis test for the correlation and seeing how you do that. And it's all done, with the calculator, of course. The math is pretty intense, so I'm not getting into the heavy math, just the light, line stuff. And that is pretty much what the plan is today. It's one chapter, but it's a really important one. And I want to give you some reminders. This is week 10. What's important about the number 10? Yeah, we have an exam. 10 is even, and there's always an exam in every even week. Although this is the last one that's going to be due on Sunday, because the next one will be due on Wednesday because the course is over then. But this is the last one. It'll be due on Sunday, so you have to take it by Sunday. I recommend, a little before, and so the very last minute. And that's your exam. The other things you should start thinking about, or not start thinking about, continue thinking about, is the project. And I do want to let you know, I went over the project when I talked about chapter 10. The project does not involve chapter 11, does not involve chapter 12, do not include regression analysis in the project. Okay, don't even think about it. And don't include ANOVA, don't include ANOVA, which is next week, and don't include the chi-squared stuff. Okay, it's a hypothesis test for difference between two means. Okay, so that's what the project is supposed to be about. So that is the plan for today. Are there any questions anybody has? Any questions? Okay, so just let you know, I'm always looking at the chat box. So if you have questions later, you can ask, and I'll do my best to answer, of course. But hopefully everything will be figured out. So now I have a question for you. I have two questions. The first question is, and you have to answer both of them because there aren't that many of you. Okay. How many miles have you ridden a bicycle in the last month? And how many miles do you live from your college? And I want you to answer both. The first and the second. If you want, you can separate it by comma. And I'm going to answer too because we don't have very many of us, and I want to make sure we have a big enough sample size. So put in the chat box, all of you. There aren't very many. And I'll start typing the data. Maybe I'll even type mine first. I have actually not ridden a bike that much in the last month because it's winter time. So there's two questions. You have to answer both of them. So I have ridden a bicycle about 10 miles, and I live 1 mile from my college. We have someone else who has ridden a bicycle 1 mile, and they live 2.45 miles. Again, everybody has to answer. Put it in the chat box. This is not an embarrassing question. You should be able to answer this question. Okay, we have someone who has not ridden a bicycle at all, 0, or you rode like 1 block or something. And I'm going to say that's 2.4. So I'm a 2.4. And does it count riding on an exercise bike machine? Yeah, we'll let it count just for fun. And again, just guess. I mean, no one knows exactly. I don't know if it was exactly 10 miles for me. So how many miles have you ridden on a bicycle last month? And how many miles do you live in your college? Do you live from your college? Put them in the chat box. Okay, 10 and 226. Whoa. It's a long way away from a college. A lot longer than me. Okay. I'm the shortest, but it's my job, so I wanted to make sure I lived real close when I moved here. Okay, so that is what we have. Okay, and what we want to do is we want to do regression analysis. Okay, and to do that, we're gonna pop this into the calculator. Which calculator number do you think we're gonna use? Yeah, 25, regression analysis. And you should get excited. We only have one more, and that's next week. Cyclic regression analysis. And you can either do 1 point at a time, or you can just copy and paste the x's and the y's. Our x's are 10, 1, 0, 10, separated by commas. And our y's were 1, 2.5, 4, 2.4, and 226. I'll copy and paste that. And then I hit plot points. And here we have it. Okay. And you'll notice what we have is we have just 4 points. There aren't a lot of us here. We only have 4 points. And you'll see that these points graphed like this, that's called a scatter plot. Any questions on that? So that's called a scatter plot, and that is the points in the x and y plane, where x is the answer to the first question, and y is the answer to the second question. Okay. And here, by the way, we have an extreme outlier way up here compared to the other three. And that's going to mess things up in terms of, getting good what's called regression analysis. But hey, we have what we have. Okay, any questions so far? Okay, we have R, which is about 0.57. Good enough for now. We have R squared, which is the square of R. And you could do it without a calculator, but might as well do it with it. I'm going to go two decimal places, which is usually best. And that is 0.33 rounded to two decimal places. Any questions at all on using the calculator? Any questions? Okay, so now let's talk about what these things mean. And here's what we have. So again, R was 0.57. When I prepared, I obviously did not know what R was going to be. Okay. So in this case, we can say the following. Okay, for college students who have ridden in college, I'm going to say people because I'm not a student. Just wanted to make sure we had enough points. For college people who have ridden their bike a lot of miles, there is a tendency for them to be farther from their college. But since the correlation is not that close to 1, it's 0.57, the highest correlation you can ever have is 1. Okay? The lowest you can have is -1. You could also have 0, which they tell you different things. But the correlation is not that close to 1. It's not that great a predictor. It's not a very good predictor. Any questions on that idea? Whereas if R was really close to 1, then we say that the first is a very good predictor of the second. Or in this case, it would say the distance that you live from let me see, what did I put this in? The number of miles is a good predictor of how close you are to the college. Okay, or vice versa. You can go either direction, it turns out, for predicting. Any questions on that, kind of the idea of R? And we'll get into more of these later. Any questions? Okay, now comes the interpretation of R squared, which tends to be even harder. We could say there's a large variation. Remember, in our class, variation is a standard deviation of the number of miles students live from their college. Okay? So in this case, there's a very large variation. But if we only look at students who all have ridden their bikes in the same number of miles in the last month, then this variation on average tends to decrease by 33%, which isn't a huge percent decrease, but it's a little bit. So that's kind of the template for interpreting R squared, is there's a large variation in the first variable. But if you only look at data values at which the first variable is all really close to the same, then that variation will drop by the R squared percent, turned it into a percent. Any questions on that? Okay, R squared is important. Okay, and we'll see R squared is pretty small here. It's 0.33. And if you look at the points, we have some points that are very far from the line. Do you see that? Especially on this right-hand side, there's some points very far from the line, which means it's not a great predictor. Any questions on that? Okay, so again, R is called the correlation. R is always between -1 and 1. So -1 is the smallest correlation. That means as the first goes up, the second one tends to go down if we have a negative correlation. Whereas 1 is a positive, the highest positive correlation. That means if we have a high positive correlation, that means as the first variable goes up, the second variable also tends to go up. Okay? If you're right in the middle at 0, then if you know about the first variable, it tells you nothing about the second variable. Okay? Or it means that the points don't look at all like lying on a line. Okay? Just note the sign, SIGN of R, is the same as the sign of the slope. So again, if we look at this picture, we see that the line is going upwards from left to right, has a positive slope. And R is positive. That will always coincide. Where R squared is always positive because squaring a number makes a positive number. But so the positivity, whether it's positive or negative, makes a big difference for R. And then how close or far from 0 you are makes a big difference. Any questions on any of this? Okay, so that's really important. Really important. All right, let's see if you can think of a real life example of 2 survey questions. Okay, they could be measurements instead of survey questions, where R is equal to 1. So you can put in the chat box an example where R is going to be exactly perfectly 1. Pop in the chat, give you a minute or two. But see if you can think of something where R is perfectly 1. I'm watching the chat box. So come up with an example. And if you're watching this as just a YouTube video, let's see if you can just write it down on paper. But those of you who are here, let's see if you can think of where R is exactly 1. When will the correlation be exactly 1? Watching the chat box. Hopefully you'll put something in. So what would the 2 survey questions be? Hopefully you'll come up with something. I'm giving you a minute or two, but it shouldn't take that long. You don't have to do the survey questions. You just have to think about a couple questions where you end up with an R exactly 1. So when is there not variation? Variation maybe is what you meant? Yeah, that's not when R is 1, by the way. I mean, example, if there's no variation at all, then you don't do regression analysis, by the way. That would be if you looked at something like, I don't know, how about if you looked at what's the radius of a professional baseball if you look at many baseballs? And then if you looked at the that would be where there's no variation because every professional baseball has the same radius because there's a rule about it. Does that make sense? So it's not about having no variation, but it's a reduction of the variation. Yeah, it's a reduction of variation when R is 1. So it's a perfect reduction of the variation when you happen to know the first variable's answer. Let's see everyone jumping in. Should I do an example since no one else is coming up? Maybe I'll put one in. How about question one? Q1 is how tall are you in inches? And how about Q2? How tall are you in centimeters? Okay, that would have a correlation of exactly 1 because if you know how many inches a person is, you know exactly how many centimeters they are. Does that make sense? Okay. Given that you remember the formula to go from inches to centimeters. But because there's a formula. You see, there's no variation. Once you know, if you have people that are all exactly the same number of inches, then they're also exactly the same number of centimeters. Any questions on that? Okay, but if you look at all people, there's a pretty big variation in height. But not all people that are the same number of inches, there's no variation in their number of centimeters. Any questions on that? Because no one was coming up with any good ideas. Do you see how that works? So that'd be an example where you know exactly based on the first variable, you can get to the second variable. There's no variation. Any questions? Okay, let's do another example. So I have that written down already. Now, if you can think of a real life example of two survey questions where R is very close to 0. And by the way, it's not going to be the bicycling and the distance from the college because R was not close to 1. It wasn't close to 0. So that doesn't work. So you can come up with one where R is very close to 0. Let's see if you can put in the chat box. So think of two survey questions where R will be very close to 0 or two measurements. So a 0 correlation or really close to a 0 correlation. So I'll give you a minute or two. Shouldn't be that hard. Come up with some survey questions. See if you can come up with one. An example of two survey questions where R is very close to 0. Okay. Okay, two survey questions, don't forget. So I got one person with two. How tall are you in inches? And how many movies have you watched? Okay. I'm not quite sure if R will be close to 0. I would say R would only be close to 0 if you're talking about adults. Because the problem is, if you include children, then if you're really young, you've probably watched almost no movies. Does that make sense? But if you're older, you've watched more movies. So as one increases, the other tends to increase. Do you see that? Now, if you only look at adults, that might be a little better. I have no idea whether height has anything to do with number of movies watched for adults. Okay. And the other one, there needs to be two survey questions, not just one. Regression analysis has to have two quantitative variables. Okay, so two questions where the answer for each of the question is a number. So a number and then another number. Does that make sense? So hopefully you see the how tall are you and how many movies. I think that might work for adults, but it wouldn't work for if you include children. Hopefully you agree with that. Because if you are really tiny, like that tall, maybe a foot tall, then you probably haven't watched any movies. But if you are, 5 feet tall, you watched more. Does that make sense? So it matters. Okay, let me give you my example. I think I have it here. Okay, so what is the temperature in South Lake Tahoe? And what was the total number of points in the soccer game at the high school soccer game in New Zealand? Okay, so notice those would have like no correlation at all. If you knew what the temperature was in South Lake Tahoe, that's not going to tell you about the soccer game in New Zealand. Is that clear? Okay, so that would have a very close to zero correlation because they have nothing to do with each other. Another one I like to give an example because you can visualize a scatter plot is something that especially if you live in Tahoe, if you live in LA, you may not even know. But if you look up in the sky at night, you see stars in Tahoe, at least, not in Los Angeles. But because it's too bright, too many lights in Los Angeles. But you see stars. And if you look at, say, east-west versus north-south, basically you're looking at the scatter plot of stars, then there's no correlation. It's not like they all lie on a line. Is that clear? They're all over the place. Any questions on that idea? Okay, so now the third question, let's see if you can answer. Come up with an example. Now, two survey questions where the correlation is close to -1. See if you can come up with two survey questions as an example, or two measurements where the correlation will be close to -1. And there are a lot of examples. Let's see if you can do that. There's some that are exactly -1, but there's some that are close to it. And exactly and close to are pretty different, by the way. Exactly means you can actually do the math and come up with the exact answer. Close to means that as one goes up, it's really clear the other one tends to go up too. So let's see if you can come up with two survey questions where you get really close to -1. Pop in the chat box. So I'll give you a minute or two. Shouldn't take too long. Just a little typing. Okay, there should be two questions. And I'm guessing you didn't mean the one a long time ago about siblings versus leave blank on the exam. Because that would be probably close to zero. How many siblings do you have and how many questions do you leave blank on the exam? That I don't think siblings have anything to do with questions on the exam that you left blank. So let's see if you can come up with two survey questions where you have an R close to -1. Not seeing y'all jumping in. Should I do it? Okay. So how about how many cigarettes a person smokes each day and how long they live? Okay, and hopefully you know this. If you smoke a whole lot, what do you think is going to happen to you in terms of your lifespan? So hopefully you know, hopefully you've been taught this. If you are a heavy smoker, what's going to happen to your lifespan? Well, not 100% certain, but often. There's been lots of statistics on this. Yeah, you're going to have, you have a much higher chance of dying younger. Does that make sense? So, how many cigarettes a person smokes, if you increase that number, how many cigarettes, the lifespan decreases. And remember that we have a negative slope. As one goes up, the other goes down, or at least tends to go down. Doesn't mean that someone who smokes none will live for sure a long time, but there's definitely a correlation. And there's been plenty of um, data analyses, studies where they've shown that there's a negative correlation. Okay, and hopefully you've been educated enough to know that smoking often makes you die younger. Any questions at all on those examples? All right, so now it's time to talk about R squared. Okay, R squared is the square of R. Okay, but it's more than that. It's best to make it a percent instead of a decimal. So in other words, you want to think of it as a percent because it's easier to interpret as a percent. And as I mentioned as an example, but here's more of a template, the variation in the y variable is considered large. But if you just look at the y values that all have x values that are almost the same, then on average, the variation is reduced by the r squared percent. So in our example, we had an r squared of about 0.33. So that meant that, hey, there's a big variation of how many miles people have ridden in the last month. But if you only look at people who have all ridden about the same in the last month, then that variation will go down, typically by an average of 33%. Any questions on this template? Any questions? Okay, so here's another example. If you look at city population size in thousands versus crime rate per thousand, okay, then R is negative 0.36. So what we can say is there's a weak negative correlation between city size and crime rate. Okay, I just want to let you know it's closer to 0 than it is to 1, or -1 in this case, and that makes it a weak correlation. Is that clear? Whereas if you're very close to 1 or you're very close to -1, it's a strong correlation. So that's typically, how you want to think about it. So if you take negative 0.36 and you square that number, so that's negative 0.36 times negative 0.36, you get about 0.13, which turns into 13%. So because of that, now comes a template. There's a large variation in crime rate from city to city. But if we only look at cities that all have similar population sizes, the variation in crime rate is reduced on average by 13%. Any questions at all on this example? Any questions? Okay. Again, I don't know where you're all from, but let's see if you know something. What do you think the most important statistical analysis in Tahoe is done? In this college is Lake Tahoe Community College. What do you think the most important statistical analysis that is done? Any ideas? If you live in Tahoe, you have a good chance of knowing. forest, hmm, not that important. This is special to Tahoe, and there's forests all over the place. Any ideas? Yeah, Clarity of the Lake. So let me tell you a this is I'll say it's a story, but it's real. This really happened. And this happened about um I think 26 years ago, something like that, a long, long time ago. And that is there was a meeting. Okay, and there was a meeting in Tahoe. And in that meeting were some very important people, including the President of the United States, okay, President Clinton, including the our Congress people. I'm not even sure. I don't remember which Congress people we had then, but our Congress people and our senators and some of the congressional people, and they met in Tahoe. And in Tahoe, they were given a presentation of the clarity of Lake Tahoe. And one of the cool things, this was a very long time ago, but it was still really cool. And that is one of my statistics students was there with them. Now, she was actually serving them lunch because she worked at the place that they were eating at, the restaurant they were eating at. And she actually got to watch it. So she told me all about it. So I know that this happened because I heard all about it. It was really cool. And what they did is they presented to the president and the senators and congress people the statistics of Lake Tahoe. Okay. And you may or may not know, but every year they measure the clarity of Lake Tahoe. Okay. And what they do is they take what's called a Seach dish, which is like a little plate, a white plate that's connected to a string, and they let it drop down and they measure how deep it goes down until they can't see it anymore. Does that make sense? And they do it on days that are a little cloudy so that the sun isn't shining on the lake too much. So they can really see down at the bottom. And one of the coolest things is I talked to the people in charge. The ones who do this are at UC Davis. They're the ones that do this science. And, I asked him, well, one measurement's not enough. And I asked him, how many measurements do you take each year? And what they said made me smile so much. Do you know how any guess on how many measurements they take every year? And the hint is it feels like they took my class. Any guess? Let's see, I'll jump it in. I say it'll make sense. Okay, you don't want to guess? Okay, the scientist said they take 31 measurements because they want to make sure the sample size is large enough. So it's like they took my class. They learned that number. Isn't that cool? So this isn't just me telling you. This is real. Okay. And then they take the average of the 31 measurements, and the average has a somewhat normal distribution. And because of that, regression analysis is like dead on good. And here's what they got. This is a picture and the data, and this shows the CTDIS, the depths of lake clarity, versus the year. Okay, and this goes till around the year 2000. Okay, they started around 1968, I believe it was, and they measured it every year. Okay, and we look at that and we can see that kind of the way they drew this looks like a scatter plot, doesn't it? All right, this might be a little bit of a trick question, but we'll see. Do you think the slope of the regression line is positive or negative? Is the slope of the line positive or is it negative? What do you think? So we have the scatter plot. You see it goes up and down. But if we look at the whole scatter plot, the best fitting line to this whole thing, do you think it has a positive slope or a negative slope? Put in the chat box. What do you think? Okay. Here's what you didn't hear. Is I told you this is a trick question. Okay, it's a little tricky because look at the y-axis. Here's 15, 20, 25, 30, 35. And again, UC Davis did this. So it's upside down. It's actually a negative slope. Because as you go up, it's going down in the meters, not up in the meters. Do you see that? Tricky. Okay. I would never do that to you on a test, by the way. But I figured this is real. If you go online, you'll find this online. If you ask for a picture of a depth of lake clarity, this is one of the first things that will happen. And here is the data. So here's 68, 69, 70, 71, 72, all the way up to 99. And that was the year. So first thing, I'm going to refresh my screen so that I can erase all the data. I'm going to put that in for my X values. X is the year. We call that the independent variable. And then Y will be the depth of lake clarity. And you can see in the year 1968, you were able to see 32 meters down, which is a long way down. But in the year 1999, you can only see 21 meters down, which is still pretty long, but not nearly as long as 32. So I'm going to put that in the Y values, copy and paste, and I just hit plot points. Okay, my calculator is not a trick question like that other graph was. This actually tells you and shows you with X and Y axes that are more reasonable. And you look at this and you say, yeah, it kind of feels like it's going down a bit, doesn't it? But you'll notice, for example, if you look from, 1981 or so to 1984, lake clarity got a lot better, right? So I want to let you know that just because it tends to go down does not mean it always goes down. Is that clear? Okay. But you look at the line, and the line is definitely sloped downward. Any questions at all on this example? Okay. We can look at R, negative 0.85 about, and we look at R squared, about 0.72. We can also look at the equation of the regression line, and that is Y is equal to about 45.6 plus or minus, because it's a negative sign, minus 0.25x. Okay, so we have this equation of the line. We have R squared. We'll get into the hypothesis test in a little bit. So now we can look at this equation. First thing, what's the slope of this line? Y equals 46 minus 0.25x. What's the slope of the line? Very important for you to know this. Basic algebra. Very basic. Doesn't necessarily mean you remember, but it's very basic. So how do you find the slope of this line? It should be really easy. What do you get? Put it in the chat box. Okay, it's not supposed to be a hard question. What is the slope of the line? Y equals 46 minus 0.25x. I don't see you all putting it in. This isn't supposed to be tough. Okay, so if you remember, the slope is a number in front of x, including the sign. So it's negative 0.25. Okay, in general, a template is the slope of a line is a rise over the run. Rise over run. Okay, it's a change in y when x changes by 1 is another way we can look at it. Thus, if x is increased by 1 unit, then y is predicted to or tends to increase by the slope number of units. Here our slope is negative 0.25. And it's easier to write this as a fraction, so we can think of it as rise over run. And I'm going to write this as negative 0.25 divided by 1, or over 1. So the rise, that is the y-coordinate change. The y-coordinate was lake clarity, how far down you can see. And that is the numerator, which is negative 0.25. So the rise is negative 0.25 meters of clarity. The run, that is the independent variable, the x variable, and that was number of years. So the run is 1 year. Any questions so far? Okay, so now we can interpret the slope. We could say for every 1 year, for every year that passes on, average, the lake clarity has tended to go down because of this negative sign by 0.25 meters. Any questions at all on this interpretation? Is that a good thing or a bad thing? Every year that passes on average, lake clarity has tended to go down by 0.25 meters. Good or bad? What do you think? Yeah, it's terrible. Okay. The lake's getting worse and worse and worse, at least at that year. It was going down a quarter of a meter on average every year. Okay. Just note the y-intercept is a value of y when x equals 0. Okay. If x equals 0 has no relevance or is far from the data values, or if the value of the x-intercept has no relevance, then the y-intercept has no relevance. Otherwise, the y-intercept is the best prediction for y when x is 0. So in our case, we can say that the best prediction for lake clarity in the year 1900, because that's zero, because these numbers were the years after 1900, is 45.6, because that was the y-intercept. 46 or 45.6. Okay, meters. Okay, on the other hand, if you look at our data values, the very lowest data value is 68, and the highest is 99. These are nowhere near 0. So, in particular, the y-intercept really isn't a good prediction at all. Does that make sense? Because it's nowhere near the data values. All right, let's do a different example than this one. What is the best prediction for lake clarity in the year 2026? So this year, we're in 2026. Hopefully you know that. And we got to figure out what the best prediction is. So that's where the regression line helps us out. What that means, and 2026, by the way, is 126 years after 1900, because our 0 was 1900. So what we can do is we can pop in 126 into the equation. And when I do that, I can go to the calculator. scientific calculator. Pop it in. And I get about 14.6. Okay. Now remember that at the beginning, it was 32. Long time ago, 28, 32, 30, 28. Are we okay if the lake clarity is 14.6 if it used to be 32? What do you think? Yeah, that would not be okay. So here's the good news. The good news is the President of the United States actually understood statistics. That's important. So the President of the United States at the time was able to watch the presentation, understand that this was scientific data, okay, with, professors and researchers. No one's cheating or anything like that, no lying. This was just scientific data. And the President of the United States and Congress said, we can't let this happen. Okay, we can't let Lake Clarity keep going worse and worse and worse in Tahoe. That would be an environmental disaster. So what they did then is they passed a law and they put in a lot of funding to help. And I'll talk about that in a bit. But before I do this, couple more things. One thing is you cannot use cause. Okay, and notice something you may not even have thought about before, but the word because. Notice part of the word because is cause. So do not ever use the word cause. Do not ever use the word because when you're doing regression analysis. Okay, not just because I'm going to take off lots of points, which I would, but also because it's wrong. You also can't say, if this happens, then it will go down. You can't say that with just regression analysis. You can only talk about on average, there's a tendency. Okay, so the next thing is hypothesis testing. Okay, so in our class, we're going to keep it this way. We're going to keep it simple. Okay, if you take more stats classes, then sometimes it'll be a little different, but for our class, I want to keep it simple. Our H naught will always be right here. How do you read this letter right here? Who knows? The hint is it's a Greek letter, and there's a good chance you don't even know what it is. It's a Greek letter, though. Anyone know? Here's a kind of a fun hint, nothing to do with science or anything, but people who are, actually measuring the depth of clarity in Lake Tahoe know about this letter because of a funny thing. Anyone know? Okay. Do you think you're going to drive to the middle of the lake, by the way? Do you think that's how people get to the middle of the lake? They drive? No, of course not. They row their boat. Row, row, row your boat. So the way you read this is row. R-H-O. Yeah, so this is rho, which is the Greek letter for R, by the way. So rho, it looks like a P, but it's actually Greek for R. Rho equals 0, which means the null hypothesis is that there is no population correlation between the two variables. And then H1 is the exact opposite of rho equals 0. It is rho is not equal to 0, which says that there is a correlation between the two variables. Okay, and by the way, You have three choices. In our class, we're always going to be doing not equal to. So that'll be the default. And you'll notice here's our p-value. Is the p-value 9.67? Is that the p-value? Rounded to two decimal places? Is that the p-value? Yeah, definitely not. Do not make that mistake. P is a probability. It can never be bigger than 1. You have to look over to the right and see this E negative 10, which means you need to move the decimal over 10 places to the right, to the left, I mean. The first just moves it here, and the other 9 places put zeros in. So by doing that, here is the p-value. That's 0.00000000967. Tiny, tiny, tiny p-value. There is very strong statistically significant evidence. You've seen those words before, but now it's very strong because it's like tiny, tiny p-value to support the claim that there is a correlation between year and lake clarity. Does that mean that every year the lake clarity goes down? What do you think? No, it does not mean that. But on average, there is a tendency for the lake clarity go down per year. Do you see that? So be careful. Okay. Okay. And again, do not use cause, do not use because. Okay. Do not use if, then, it will. Those are just bad words. Because sometimes you might even think that it might be a, causation kind of thing, but in statistics, you can never say that something caused this or something affects this. You can't do that. Okay. Okay. Even if you think it might be true, if all you've used is statistics, that's not enough. You have to have other science. Okay. So lots of things. So for example, if you look at children who have been beaten as little children, okay, and then you look at how many times they beat their child when they're older, then there's actually a strong correlation. I watched a video on child psychology. I think it was Yale, and they did the full correlation. Does that mean that beating your child will cause them to beat their child when they're older? If you know, say the correlation was 0.98. Can you say that? That child is beating their children because they were beaten as children. Okay, you cannot say that from just statistical analysis. It's possible that, hey, maybe that child was a real aggressive kid and they got beaten by their parent because the parent needed to. And then when the child got older, they were a real aggressive parent and they beat their child. Who knows? We really don't know. Okay, and that's what the professor said, by the way, in Yale. I've watched this video, and all you can say is that, hey, children who get beaten often tend to beat their children often when they become adults. You can talk about that as a tendency, not a causation. Is that clear? Okay, those are really important words to avoid. So the only way to get causation is to also bring science involved too. Okay, but not just math and statistics. You have to have science. And then sometimes you can talk about cause because of science, but the stats is not enough. Okay, just to let you know, as I mentioned, they passed the law and they put a whole lot of money into helping the lake clarity. Okay, in all kinds of ways, by the way. I'm not going to get all the details because this is a statistics class. It's not a class on, you know, environmental science, but I've studied it all, but I can tell you it all happened. And now Again, if you looked at the original graph, I purposely stopped it at 1999 because that's when they passed the law. But they didn't stop measuring the lake clarity, they kept going. And let's take a look. Now, this is the most current lake clarity graph. This goes like till last year, basically. And notice what happens after 1999. What do you notice about the scatter plot if you ignore this left-hand side and you only look from 1999 to now? What do you notice about the scatter plot? What do you see? What can you say about the correlation post 1999? Whereas pre-1999, it clearly went down. Okay, remember the graph going up meant the numbers go down in this case because this is an upside down graph. But what can you say about the scatter plot post 1999? Any thoughts? You can't see it. Notice that it goes down and up and down and up and across. There's no correlation anymore. Do you see? From 1999 to now, you can't visualize and just see, it looks like it's going better, or it looks like it's going worse. Now it just goes up and down. Do you see that? And it worked. This law made a big difference in lake clarity. Instead of going up like that, it stopped and then flattened out. Now it still goes up and down. Do you know why it goes? It doesn't just stay every year the same. This is science, not statistics. The reason why it doesn't actually, it turns out, and I guess in one word, what makes it some years to go really good lake clarity and then some years to go really bad lake clarity after they've dealt with human issues? And that's what this post 1999 was, is dealing with getting rid of all the human issues if they could. Any guess? Let's see, I'll jump it in one word. Weather. Weather. So if you have a whole lot of snow and rain, then you have a whole lot of soil that goes into the lake and you lose clarity. Whereas if you have a lot less, then you have good clarity. Okay. So that's these ups and downs. So again, you can say that if you look from, 1968 to 1999, R squared or R was negative 0.36. Our R squared was, sorry, R, it's over here. Let me go here. I think it's easier to find it. There it is. So our R squared was about 0.71 or 0.72. So again, you get a reduction in how much the clarity is changing, the variation in clarity by 72%. But then the other 28% is based on other factors. And that main factor in Tahoe is weather. And that has some you get changes in clarity because of weather. Does that make sense? So this is all kind of environmental sciencey stuff. So just a note, there's our graph. Let's look at one more example. Look at years of successful education after 10th grade and salary in thousands of dollars at 30 years old. And here we have data. And we can do the same thing. Let's pop it in. So I'm going to copy and paste all our numbers. Notice we have somebody who went 12 years of, successful education after 10th grade, and then someone who dropped out of high school and didn't have any education after 10th grade. So it's all over the place. And if I hit plot points, there we are. Notice as the years increase, we definitely have an increase in the income. We have a y equals negative 27.3391 plus 16.4 or so. We have r is 0.9, r squared is 0.82. So pretty good correlation. Okay. We have our hypothesis test. Our p-value is very small, 0.0001. If the p-value is large, then that tells you don't have any evidence to show there's a correlation. And pretty much if there's no evidence to show a correlation, you just say this whole thing is useless. Don't use the regression analysis to talk about anything other than we don't know. Okay, so it's very important to have a low p-value. Okay, any questions on that? So if you interpret R, there's a strong positive linear correlation because R is 0.91, which is a big, strong correlation, positive linear correlation between the number of years of successful education after 10th grade and the salary at 30 years old. Okay, to interpret R squared, which is 0.82, there is a large variation in salaries at 30 years old. But if we look at 30-year-olds who all had close to the same number of years of successful education after 10th grade, then that variation on average tends, that word tends has to be there, to be decreased by 82%. So make sure you pop that. Maybe I'll put that in red just so you know that's a word that you need to have or you lose points, by the way. And you also need to have that you're talking about an average. Okay, it's not any particular, it's an average. So on average tends to be decreased by 82%. Put that in your notes that when you're interpreting R squared, those words have to be there. You don't want to lose points. Okay. And the rest is template, but especially those words have to be there. The rest, you have to have the idea. Okay, so the y, the equation of the line was negative 27.3 plus 16.4x. Okay, so if we want to interpret this whole line, let's say you want to predict at x equals 6. So in other words, if someone has 6 years of education after year 10 of high school, so that's basically, they finish in 4 years, it's a bachelor's degree. Okay, so if you plug in 6, I got 71. So our best prediction for someone with 6 years of successful education after 10th grade is they will earn a salary of $71,000. Okay, notice this is just a best prediction. You can't say that, hey, you will earn $71,000 if you have 6 years of education after 10th grade. This is only a prediction. Okay, if you want to interpret the slope was 16.4. So for every additional year of education after 10th grade, on average, the salary tends to go up by $16,400. Any questions on that? Notice it's an average and a tendency. It doesn't mean it's always going to happen. Okay, the y-intercept really doesn't make any sense because our y-intercept is about negative 27. That'd be in thousands of dollars. And no one makes negative $20,000 a year for work. Negative doesn't happen. That's not what jobs are. So the y-intercept in this case doesn't really have any relevance. Okay. Any questions? Any questions at all on this regression analysis example? Okay. Any questions? So we've kind of gone through all of this. And then, by the way, if we look here, our p-value is small enough, so there is strong, it's very small. There is strong statistically significant evidence to conclude that there is a correlation between number of years taken in education after 10th grade and salary at age 30. Does not mean everyone makes a lot of money if they've had a lot of education, but there's a good, strong correlation. Have I lost anyone? All right, secret word. The secret word is reduced. Okay, because we saw that we said if we had a negative slope, then for every increase of 1 for x, y on average tends to be reduced by whatever that slope was without the negative. That's why reduced. Okay, so that, hopefully you put that in your notes, reduced, reduced, reduced. And that's pretty much what I need to say about regression analysis. This is used a lot. You're going to see it in lots and lots of research papers, and it's really important. It's used for all kinds of things. It's also used for economics a lot too, for money. Okay? Because you want to find out how to make money. So as you do one thing a lot of money goes up. And the education was one of them, but there's all kinds of other things where you can make money. Okay, or lose money. So that's just a note. I think I'm going to call it a webinar. I'm going to stop the recording. But thanks for coming. Well, next week's will be on Tuesday, by the way, and that'll be our last one. So not tomorrow, by the way. It'll be a week from tomorrow, so it'll be Tuesday, the 22nd. I do want to mention one more thing. I forgot to tell you. On Friday, I will not have student hours. So if you log in, I won't be there. I have a conference I'm going to because Saturday is the most important holiday of the whole year, which is most important to me. I don't know. No, that's not a holiday. That's just a birthday. My birthday's not this month. Should I tell you? It's funny. It's Pi Day. 314, 3.14. Saturday is Pi Day, March 14th. So I have a conference to go to, and it's going to be starting on Friday. So I'm going to be missing my student hours. Just let you know that. Okay, so now I'm going to stop my recording.